Okay, today we're going to talk about piles in sand. Yeah. So when we're basically estimating the bearing capacity or the reaction of the pile, basically. So piles in sand or on sand, to be more precise, on sand, piles on sand. Yeah. So we're going to deal with one equation today. Q allowable equals QP, which is the end bearing, plus QS, which is the skin friction, over a factor of safety that's usually ranges from 2 to 3, sometimes like you're pushing it 4. But today, for our purposes, we're going to use 3. So we talked about 2 points on this equation, right? QP and QS. So QP basically is concerned with the reaction of the pile on the tip of the pile here, or what do you call it? The bottom of the pile here. Yeah. So basically, this is QP. Yeah. It's going to be a distributed load that we're going to multiply by an area and get the point load. So this gives you Q. And this one is Q, small. Yeah. QP, Q capital P. Yeah. So this is the area of the pile, basically. If this is a pile here, let's take this as an example. So let's imagine a high displacement pile that's solid, that's going to be driven, hammered, basically, on the soil. So we're going to have what? The surface area, basically. So this area that I'm telling you is going to be multiplied by an area. It's going to be the surface area, which is called AP. Yeah. And we have another parameter contributing to the strength of the pile, which is the skin friction. The skin friction is concerned by this that I drew in red, if you could see, yeah? And this is along the whole parameter of the pile. So if we take a top view of the pile, you see these lines that I drew now in black and blue? These are the ones that are concerned with the parameter of the pile, therefore to the skin friction, which is the contact area with the soil. If this is the pile, there's a contact area around the soil, which is the parameter times the length. Okay, now we're going to move to an example, yeah? Yeah, let's talk some theory first. So basically, to calculate end bearing, you're going to use this equation, yeah? The lesser between these two values. We're going to talk about this in particular. So AP Q dot, we know how to calculate. This one, QP, the Q naught is from the soil mechanics, basically, regular stress. And we have NQ, which is calculated from either this graph or this table. And again, if you know me, I only go with tables. Yeah. If I'm given a choice. Yeah. And should be basically the lesser between these two. The other value has something called QL or Q limiting, which is calculating using this formula. But PA here is 100, which is atmospheric pressure, which is 101 point something, but for our purposes, we choose 100. And Q is the same you find from this table. And tan phi is basically for the layer. So in my question later, I'm going to tell you which layer, which is the end layer, the basically, where did the pile stop? There. Okay, we're going to go to the example now. All right, so we have a pile basically driven, yeah, high displacement pile, so it's solid. The diameter is 0.81. So he wants us to calculate Q allowable. So we say Q allowable equals QP plus QS over factor of safety of 3. Now I'm going to solve each of these problems individually, right? We said that for QP, basically, for QP, we have area of the pile multiplied by Q multiplied by NQ star, the lesser between the two of these, APQL. Yeah, so I'm going to solve each problem individually, basically. So area of the pile equals pi d squared over 4, which equals pi multiplied by 0.381 squared over 4. I'm going to do this later when I calculate by the end. Q naught equals basically, now here I have to calculate all the layers, yeah? I remember I have a groundwater table. So for the first 3 meters, I have these material properties. Then for the area touching the water, I have this material property. So this soil is the same, but it has two densities. One is dry and one is saturated because I have a water table, and whatever is under the water table is submerged. Yeah. So basically, for the first term, there's going to be 3, which is the length multiplied by 15.7, which is gamma, plus I have basically water, okay, 3 again, multiplied by 18.2, which is what gamma sat, minus 9.81, plus I have the rest, which is basically this now, which is 15 multiplied by 19.2, which is the gamma of the layer, minus 9.81. This all gives me 213.12 kilonewton per meter squared. Okay, now I solved Q's problem. Now NQ star, we said it is concerned with the angle of friction, right? The angle of friction is the angle of friction of the layer that the pile is resting on. Yeah, so it's going to be 4 phi equals 40. This equals now, we go to the table again. I did mark it already, 346. Cool. Now I'm gonna basically, since I know the formula of this as well, I'm gonna like put them in one go immediately for like, because I don't wanna make the video too long. So pi, which is the area of the pile, pi multiplied by 0.381 squared over 4 multiplied by Q naught, which I calculated as 213.12, multiplied by, what else, NQ, which is 346. All right, should be less, the lesser between the two of these, AP, which is pi, multiplied by 0.381 squared over 4, multiplied by Q limiting, which is 0.5, multiplied by PA, if you remember, 0.5, PA, 0.5, QA, and Q tan phi, multiplied by 100, multiplied by NQ, which I calculated 346, multiplied by tan 40. Now, this gives you two values that you're going to choose the lesser of. So you're going to get 8,406.98 lesser or equal than 1,655. So now your QP is the lesser between these two, so it's going to be 1655, and you put it in a box, and you put some stars, yeah? So you know that you actually accomplished something today. Okay, this is for QP. Now QS is a little bit complicated. So I'm going to clear this picture for now. Now we calculated. I'm going to clear this picture, so I now could talk about the skin friction, basically. So yeah, so we go to the skin friction. So the formula for skin friction, we're going to talk about skin friction individually now. So we go to the skin frictions, yes. So basically, when you're dealing with these type of problems, yeah, you usually have to follow this thing. So I increase in stress, basically, my F friction, which is Fs or F, the frictional stress, it's going to be what? Fs increases linearly until a point, then it goes constant, as you can see here. It's going to increase linearly to a point, and then it's going to go constant. What is that point? This point is 15D. Yeah, it's 15 times the diameter. So later I'm going to actually do this. Yeah. And then you have this formula that you're going to calculate with, which is basically K naught or K sigma naught tan delta. I'm going to talk about K first. So K is dependent on the type of the pile. So in our example, we're driven displacement piles. displacement piles are high displacement piles, which are these. Usually you either go with 1.3, which is in the range of 1 to 1.5. There is no right and wrong here. You could choose whatever. I usually take the middle ones, basically, which is 1.3. Yeah, this is the high displacement pile. So now we solved K's problem. Sigma basically is dependent on the layer. It's basically the sigma we use to calculate in every bearing capacity, which is gamma times the depth or the length of the layer or whatever, yeah, however you want. Yeah, it's going to be gamma of the layer times df or L sometimes, in this example, L, yeah, which is the regular good old one, yeah, that you use to calculate for each example. This is not a new term, basically. We calculate it all the time. Now, delta, yeah, is defined as 0.8 phi, yeah. Braha's book uses 0.6 sometimes. I've seen 0.7, so it's safe to say that the range is from 0.6 to 0.8, but in this example, I'm going to use this one, 0.8, because that's what basically you're taught. But it's not wrong if you actually choose 0.6 or 0.7, yeah? Now we solved all the problems surrounding this. And if you see the QS formula, it's going to be a summation of multiple layers, yeah? So every layer has its own FS, and therefore you have to calculate QS there, which is this, which is the parameter times the length of the layer multiplied by the FS, which is the thing that's going to change. Yeah. So now I'm going to write QS equals the summation P delta L F, where F equals K naught sigma tan delta. Okay, so I'm going to say F increases linearly until 15D, which is 15 times 0.381, which equals 5.715. So it's going to increase linearly. I'm going to put like a drawing here, so I basically see that I'm going to increase linearly to a point. Then I'm going to go constant. But here I have a water table. That's the trick. So basically, I'm going to have an increase like this and another increase like this until 15D, which is because my water table is at 3, remember? And I'm going to have the balance, which is basically, this is 5.715. So this region, I'm going to go linear, then the rest is going to be constant. This is my drawing mentally, conceptually. I'm going to plug these numbers now. I'm going to find each one. Now for Z equals 0, Fs equals 0. So the first point on the graph here is going to be 0. Okay, now for Z equals 3, now I have to calculate a lot of things. So I have to calculate delta sigma at Z equals 3, which equals 3 multiplied by 15.7. Remember, this is gamma of the layer, which equals 47.1. Yeah? Why did I stop here? Because under that I have a water level, remember? So that's why I separated these two. I solved an example with you guys in class surrounding only no water table, and I didn't do this twice. But I did this twice now because I have a water table. Okay, so I calculated this. So I calculate delta now, which is equal to 0.8 multiplied by, if I remember, it was, yes, it's 32 for this layer. See, pi is 32. Pi is 32, so it's going to be 32, which equals 25.6. And K, we said, is going to be 1.3. Now I'm ready to calculate F, or F friction. Fs has many names. 1.3 multiplied by 47.1 multiplied by tan delta, which is equals to 25.6. This equals 29.336. So I go upstairs here, and I actually write here that it's going to be 29.336. Now I'm going to have to find this. I'm going to repeat this again. Why do I have 2 of these instead of 1, like our example that we solved in the first class? Because I have a water table now that is going to change the material properties. Yeah. It's going to change basically sigma. Yeah. Everything else is the same. Delta is the same. 1.3 is the same. Oh, the only thing that changes is sigma. So for Z equals 5.175, which is basically what? 15D. Don't forget, these numbers matter. Knowing what everything corresponds to is really important. And I would prefer if you'd actually write this in your papers, exams, whatever. So at Z equals 7.15, you have sigma equals 15.7. Remember, I actually have the first layer is included in my sigma because sigma is what? The increase in stress. Increase in stress. So you calculate whatever is above 2. Plus, now I'm not going to substitute. I'm going to substitute this 5.175 minus the 3 layer that I included. It equals 2.715. So it's going to be 2.715, which is the remainder of the layer, multiplied by 18.2, which is the gamma of the layer, minus 9.81, which is gamma water, because this is SAT, gamma SAT. This equals 69.9, what a special number, kilonewton per meter squared. Now I'm going to have to calculate F, yeah? F. F equals now 1.3 multiplied by the special number 69.9 multiplied by tan 25.6. This equals 43.53 kilonewton per meter squared. Yeah, so I'm gonna now plug it in my drawing. 43.53. And after that, because I assumed my increase in stress to be 15D, I'm going to have what? The layer is going to be the same now, constant. Now, when I calculate the skin friction is going to be the sum of this layer average, sum of this layer average, and the sum of this layer without the average. Okay, now I'm going to talk about something. For this layer, basically from 0 to 2.29.336, you're going to have the average of the layer. So it's going to be 0 plus 29 point this over 2. And for the second region that is linearly increasing, you do it again. It's going to be 29.336 plus 43.53 divided by 2, which is the average. Yeah, so you take the average of this layer, but you do not take the average of this layer, you take the whole thing. Yeah. Cool. I hope that makes sense because I only take the average for these slanted lines, yeah? The things that have a slope. There we go. This is slope 0. I hope that makes sense. Let me just erase this. Yeah. So now my QS, so I've done this before. Cool. So QS now, I'm going to write it in formula so you know what I'm doing. So it's going to be FS or F at Z equals 0 plus F at Z equals 3, which is the thing that I told you I'm going to have the average for, multiplied by the parameter. Remember, it's summation P delta L multiplied by F, right? So this is the F part. And this is the parameter part, which is pi D now, multiplied by L, which is the L part, delta L part, plus F at 3 plus F at 5.175 divided by 2, multiplied by the parameter again, multiplied by the length. Yeah, plus I have one last layer that I'm not going to take the average for because it's not a slanted line. I know I'm repeating this a lot, but I cannot stress it enough that it's very important to know which ones to take averages for and which ones you don't take averages. It's going to be F at 5.175 because it's all the same after that, multiplied by pi D multiplied by L. I'm going to plug numbers now. So it's going to be 0 plus 29.336 over 2 multiplied by pi multiplied by 0.381, which is my diameter of the pile, multiplied by 3 plus, again, another 3 is the length of the layer, huh? Don't forget. let me put some lengths here. Yeah, so this is 3, and this whole thing is 5.715. So this small layer here is the 2.175. Yeah, so this one is 2.175. And whatever is left, you do the balance. Basically, it's going to be 3 plus, which is going to be basically what is the length of the whole pile? You add these together. So 3 plus 13 minus basically 5.175. You're going to get 15 point something. I did all this. I'm going to plug it later. So now I'm going to have the second term, which is basically 29.336 plus 43, I think 43.53 over 2 multiplied by pi d, which is the parameter now, pi multiplied by 0.381 multiplied by L, which is 2.175, which is this layer now. This one, this basically, the thing I'm shading right now. The trapezoid, yeah? Plus now, it's going to be 43.53 multiplied by pi multiplied by 0.381. Now the length is the balanced length, whatever is left now, which is basically 15.185. Cool. 15.185, which is the remainder now. After this, now you went down 5.175, right? So it's going to be the pile length minus this, and it's going to give you 15.185. All of this would equal, I'm going to calculate each term individually in the calculator so you could follow easily and find out if I made any calculation mistakes. So 52.67 plus 118.4 plus 796.4. All of this will equal 967.47 kilonewton. Yeah, so now my Q allowable, my Q allowable equals, we said 967.47 plus whatever I calculated before, which was 1655 divided by the factor of safety of 3. This equals 874.16 kilonewton. And this is your final answer. Yeah. Now I have to comment on a couple of things. Now, when we talked about end bearing, it was only concerned with the point load. That's basically where the cursor is. So that's why I was only multiplying by the surface area here. But when I'm calculating skin friction, it's going to be the parameter. Yeah, the parameter, basically. This, if you take a section here, it's going to be something like this. It's going to be the parameter. The parameter is in meters, right? Multiplied by the length, which is in meters too. So you get a surface area of the whole pile, meters squared, which is why you get Q capital, not Q small. Because Q small is kilonewton per meter squared, and Q capital is kilonewton only. So you have to multiply by an area. For here, it's the surface area of the bottom. For this, it's going to be the parameter multiplied by the length. That's your area. Yes, and skin friction. Skin friction increases linearly until 15D. Yeah? That's why I calculated a linear range, then a constant range. Yeah, because it increases linearly till 15D. Yeah? And why do I have 2 increasing points? Because I have 2 layers, one of the same material properties, but one of them is submerged underwater and one is not submerged. So one we have gamma dry and one we have gamma sat. And sigma for these are different. That's why I have 2 values for the increase. I hope that was helpful, and good luck in your exams, guys, and take care.